Okay, so part B is now about significant tests for slope. So part A, we did intervals for slope, and now it's tests for slope. This is the homework. Okay, so when we do this kind of a test, it's very similar to what we do when we compare categorical variables. This is what, between two, these are the hypotheses for two categorical variables. There's no linear association between rho and test score for students. There is a negative association. So notice we can use beta. For this section, we don't write words. We just use symbols. And it can have a direction here that's different than say intervals. So we can just say beta equals 0. There's no linear relationship there. But then your alternate's usually like, we think there's a negative, or we think there's a positive linear relationship between the two variables. So typically you're going to have a direction there with the slope one. But it kind of depends, I guess. I guess it could be not equal to, maybe. But usually a direction. So what are the conditions? So today we're just kind of laying the groundwork for a test. So one of the things you have to get down is the conditions. So first, is it linear? Is it normal? Does it have equal standard deviation? I really like the way they said this. For each value of x, standard deviation is about the same. There's no pattern in the residuals there. Random comes from random sample or random assignment if it's experiment, and less than 10%. So same 5 conditions as the intervals, basically. So let's see. By the way, just a side note, I like these little tips. If it says the conditions are good, like they've already checked them, assume the conditions are met. So if that's the case, don't check the conditions. Just assume they're met and keep on going with things. Okay, so here's a question. Are students with longer feet typically taller than their classmates? And this seems like it would be true. I'm just guessing. So 15 high school students were selected at random and asked to measure their foot length and height, both in centimeters. Here's the computer output from a least squares regression line. Okay. Hard to tell too much just from that. State appropriate hypothesis for a test about the slope of the regression model for predicting height and foot length in the population of high school students. So let's check the conditions, right? So first let's do the hypothesis. That's what this is about, right? So we might not have enough information to check all the conditions yet. So let's see. So the null is, we don't think there's a linear relationship. So B equals 0. Beta equals 0, I should say. The alternate is, we think it's going to be a positive linear relationship. So we think beta is greater than 0. So that would be your null and your alternate there. Again, usually the null is equal to, usually the alternate is an inequality sign. And you might want to define what beta is. So beta is the slope of population regression line, generically speaking. For this problem, when the height measured in centimeters is y, and the foot length measured in centimeters is x for high school students. Again, they didn't say positive slope anywhere in there. They just said that they thought there was a positive association because if your foot is longer, they think you're going to be taller. And so that's what they were saying there. Explain why the data provides some evidence for the alternate. Well, it's actually a pretty good question. So what's the slope? The slope, according to the output, is 2.7. Is that a positive number? It is. We've got some evidence there. So that's our B. We're trying to use that to estimate beta. So we have some evidence that's a positive relationship. Is the random condition met? We're selected at random, so that seems to be a random sample of 15 high school students. Suppose the conditions are met to perform a test that beta equals, beta equals null. So this is the formula for T. So B, which is your sample slope, minus the population null, which is going to be 0 in most cases there, over the standard deviation of your sample slope. So find the p-value by calculating the probability of that with the degrees of freedom n-2. Remember, that's n-2 for this type. They have some of the formulas on there, at least for SB. You may not even need it here, though, honestly. Here's the computer output. We want to use these data to perform the test, perform that test, where beta is the slope, etc. They defined it. Assume the conditions for inference are met. We're going to assume that. Calculate a standardized test statistic and p-value. Okay, so t is going to be a fraction. You're going to take the slope from the sample, 2.7469, minus the null, which is 0 slope, divided by the SB, the sample standard deviation of the slope, which is, or residuals there, which is 0.7833. So it's always the number right next to the slope there. So then you're going to type that in your calculator and see what you get, 3.507 when you do that. So now you want to get your calculator out and go, okay, actually, let me just graph this. So we've got, the t curve, got 0 there. What did we say it was? 3.507. So 1, 2, 3. So there's 3. Way out there is t equals 3.507. So we're shading like right out there. So on your calculator, you're going to go to TCDF. So stats, distributions number 5, and there it is, TCDF. And we want to go, not from that, we want to go from 3.507, I believe, if I did that right. Upper bound, infinity, or a big number. Degrees of freedom was, for the 15, so 13 is degrees of freedom because n-2. Should be something like 0.0019. Let's see what they got. So I drew it, 0.0019. We did it right? So that's what you do to get the p-value again. Interpret the p-value. So again, you want to start generically thinking about it, assuming the null is true, what's the probability of getting a result that extreme or even more extreme than that? So in this case, assuming that the slope, that there is no linear relationship between height and shoe size, there is a 0.0019 chance of getting a slope as extreme as that or more extreme. Let's see what they said. They said, they mentioned, so there's no association between the foot length and the height of the population of high school students. There is a 0.0019 probability of getting a sample slope of 2.7469 or greater by chance alone. Pretty similar. What conclusion can you make? So because our p-value is very small, less than the alpha, 0.0019 is less than 0.05. We reject the null. We have evidence that there is a positive relationship between height and shoe size. So let's see what it said. See if they did that the same as what we've done before. The data provide convincing evidence for the slope beta population is greater than 0. So we have convincing evidence of a positive linear relationship association between foot length and height in the population of high school students. So interesting to me, they didn't reject the null here, even though it's a test. They just said we have convincing evidence. So they did go to convincing evidence because, they did reject the null. Sorry, I didn't see that up there. I was going to say, why didn't they reject the null? They rejected the null. Okay, so pretty similar to what we've done, but you're talking about the slope, right? So in this case, a positive linear association between foot length and height, which makes sense. Every once in a while, though, you see someone who's pretty tall with smaller feet, or vice versa. Okay, let's just look at a couple of quick examples here of another problem. Can taller people jump higher relative to the size of the people who aren't as tall? Research chose 20 students at random from a high school. Of that many students, after contacting these students in some case several times to get permission, they measured their height in inches and vertical jump as a percentage of their body fat. Some computer output and graphs for least greatest regression line are shown. So that looks somewhat linear and positive there. What's the appropriate hypothesis? So the null hypothesis would be beta is 0. And I think the alternate would be beta is greater than 0, right? We think there's a relationship between there, where beta is the slope of the population regression line when y is the vertical jump, and x is the height in the population of students in high school. Explain why the data provides some evidence. Well, the slope of the regression line is 0.882, right, which is greater than 0. So we think we have some evidence. Is the linear condition met in this case? It's a good question. So look at the residuals there, especially. Residuals are scattered, so yeah, I think so. Because the scatter plot shows a linear relationship and the residual plot shows a fairly random scatter, then it is in fact linear. So that's easy peasy, we got it. Same example, we want to use the data to perform a test, calculate the standardized test statistic and p-value. So let's see, so this will be, so t equals 0.882 minus 0, I guess, technically, over 0.26. So we get that t-value. It's definitely positive. You're shade that way. So let's see what they get for the p-value. So they got 0.3392 with the degrees of freedom of 18. Then they did their TCDF and got 0.0016. Interpret the p-value, assuming the null is true. In other words, assuming that there is no linear relationship between vertical jump and height, then there is a 0.0016 chance of getting slope as extreme as 3.392, as extreme as 0.882 or more. Let's see what they said there. 0.882 or greater by chance alone. What conclusion would you make? Because our p-value of 0.0016 is less than the alpha level of 0.05, we reject the null. We have convincing evidence that there is a positive linear relationship between the vertical jump and the height in the population of students. Perfect. Okay, that's your lesson for today.